In this video, we will continue to look at the preparation of organohalides, focusing on how they can be prepared from alcohols. To convert alcohols to alkyl halides, a general reaction involves treatment of the alcohol with HX, and so this can be called a hydrogen halide or a hydrohalic acid or just HX, and the product will be an alkyl halide with water as a byproduct. Here we have a few examples, and I want you to notice some of the differences in the way these reactions are represented. Here we have a reactant or starting material. Here we have another starting material or a reagent, we could call it. This is going to react together. Here it's similar, but now we have one of the reactants written over the arrow. So there are a lot of ways that organic chemists use shorthand as we are describing reactions. Sometimes you will have all of the reactants written out explicitly. Sometimes you'll have the important organic reactant and then other reagents written over or under the arrow. Sometimes additional details will be spelled out, like the solvent, whether the reaction is heated up, other additives. So we're going to see a lot of different things. For the most part, I try to keep it simple and I don't give all of the details, which you would need in lab, for example, but we don't need it when we're doing these reactions on paper. So in our first example, we have a tertiary alcohol. Remember, we look at this alcohol is connected to this carbon. This carbon is connected to 1, 2, 3 other carbons. So this is a tertiary alcohol. If this is treated with HBr, it will make T-butyl bromide a tertiary bromide, and it'll also make water as a byproduct. Another thing that we organic chemists do, even though there are times we have to write all of the details, who cares about a byproduct like water? Because as we're carrying out a reaction in lab, we're going to separate out the water by doing an extraction, for example. So often we'll just skip these byproducts because we only care about the organic species. Our tertiary alcohol could also be treated with HCl, and this is a way to make a tertiary chloride. And our tertiary alcohol could be treated with HI to give a tertiary iodide. These reactions can also be carried out on a secondary alcohol, can be converted to an alkyl halide. Here we have a primary alcohol. This can be converted to a halide, and we can also use methanol and convert that to an alkyl halide as well. So here we can see that this reaction can be carried out with several different HX and on several different types of alcohols. We're continuing to talk about our general reaction to prepare an alkyl halide from an alcohol, but let's look at some specifics. If we were to compare the different HX, what we'll find out in terms of relative rate, HI will react faster than HBr, which reacts faster than HCl, which reacts faster than HF. In practice, HF is not used by itself, and HI often isn't used for this reaction either, so we're going to focus on HBr and HCl. What does this mean then to say that this reacts faster than this one? If we were to compare the same starting material being treated with HCl to form the chloride, or being treated with HBr to form the bromide, there's a couple different possibilities. Maybe this reaction is done in an hour and this reaction takes 24 hours. Or maybe this reaction would be carried out at room temperature and this reaction has to be carried out at 50 degrees. So we will change the reaction conditions to be able to get the reaction to go to completion. But I'm not going to be writing all of those details all the time. I just want you to have an idea of how we deal with relative reactivity. If we want a reaction to happen with HCl, then we either have to give it more time, we have to heat up the reaction, we have to try different methods to get the reaction to work. Now, if we compare different alcohols, once again, thinking about the rate, a tertiary alcohol is going to react faster than a secondary alcohol, and these react faster than primary or methyl alcohols. Now, what do we do about the relative rate of reaction? Well, maybe we can react a tertiary alcohol with HBr to give us our bromide product. Maybe this one can occur at room temperature. But for a secondary alcohol to do the same thing, maybe we have to add heat. A primary alcohol, again using HBr, maybe we have to use a lot of heat to get the reaction to occur. So in lab, the reaction conditions are going to vary somewhat depending on the identity of HX and depending on the structure of the alcohol. Next, let's take a look at some experimental evidence about these reactions. So if we have an alcohol and we treat it with HX to give RX plus water, how fast does a reaction happen? Let's say we're looking at reaction A, which uses a tertiary alcohol. In trial 1, we have a certain concentration of our alcohol in HX, and a particular rate of reaction is measured. As we go to trial 2, we double the concentration of our alcohol, but the concentration of HX is held constant, and we see that there is a doubling of the rate. So by doubling this concentration, we get a doubling of the rate. This tells us that for a tertiary alcohol, the rate of the reaction is proportional to the concentration of the alcohol. Next, if we compare trial 1 to trial 3, we're keeping the concentration of alcohol constant, and we are increasing the concentration of HX, but this time there is no change in the rate of the reaction. So that means that the rate is independent of the concentration of HX. So for a tertiary alcohol, we can say that the rate is equal to some rate constant K times the concentration of the alcohol. But now let's look at reaction B, and here for our alcohol, we're using methanol. Looking at trial 1 compared to trial 2, we are doubling the concentration of the alcohol while holding the HX concentration constant, and what we get is a doubling of the rate. So we increase the concentration of the alcohol, we increase the rate of the reaction. So for a reaction with methanol, once again, the rate is proportional to the concentration of the alcohol. If we look at trial 1 compared to trial 3, we hold the methanol concentration constant, but we double the concentration of HX, and we double the rate of the reaction as well. So unlike reaction A, for reaction B, the rate is also proportional to the concentration of HX. So for a reaction with methanol, we would say the rate is equal to some rate constant K times the concentration of alcohol times the concentration of HX. Because we have different rate laws for reaction with a tertiary alcohol compared to reaction with methanol, this means that these reactions must occur through different reaction pathways. Now, for just a moment, let's stop thinking about molecules. Maybe we have a starting point and an end point, and it's possible to take pathway number 1, or it's possible to take pathway number 2. Maybe we're camping and the starting point is our campsite and the end point is a beautiful waterfall that we want to see. One pathway is to go hiking and another pathway is to swim up the river. Well, for some people, they might love hiking and they don't really want to swim. So they could swim, but it'd be a lot easier for them to go hiking. So they will follow one pathway if possible. Now, another camper might love swimming and they're not really so crazy about hiking, and so it's a lot easier for them to swim to the endpoint rather than hike. Maybe they could do it if they really had to, but it'd be a lot easier for them to just swim. So let's think about that idea of having different ways to get to an ending point, and think about how molecules often have different ways to get from a starting point to an ending point, and which route they choose depends on the compound. For some compounds, it will be easier for them to take this pathway, harder to take this pathway, so they'll go this way. But for other compounds, maybe this pathway is easier and this one requires a lot more energy. Molecules will always react via the pathway that is lower energy for them. And so what we see here is that there must be a difference in the pathway. So we would say that tertiary alcohols follow a different mechanism than methanol. And in the next several videos, we'll be looking to explain why that happens.